All right, so this thing says a 50-turn coil has a diameter of 15 centimeters. The coil is placed in a spatially uniform magnetic field of magnitude 0.5 Tesla. By the way, 0.5 Tesla, that's a pretty strong field. That's about 10,000 times stronger than the Earth's magnetic field in this room. You know? So that the face of the coil and the magnetic field are perpendicular. Find the magnitude of the EMF induced in the coil if the magnetic field is reduced to 0 uniformly in 0.1 seconds, 1 second, and 60 seconds. Okay. So we saw that Faraday's law says that d phi by dt, okay, the magnetic flux. Okay, so the magnitude of the induced EMF is d by dt, b a cosine theta. Okay, where here's the, okay, and by the way, so when you have n turns, it's n, you have to include n times b times a times cosine theta. Okay, a so b, that is theta. Okay, in our problem theta is 0. Okay, the face of the coil and the magnetic field are perpendicular, so the face, the magnetic field is perpendicular to the face, so theta is 0. So the only thing that is changing is, this is not changing, that's not changing, that's not changing. The only thing that's changing is B. Okay, so the induced EMF is NA del B by del T. All right, and the area is pi r square. It's a circular coil, del B by del T. So we'll do part A. So induced EMF, when you turn off the field in 0.1 seconds, so that's 50 turns times pi r square is 7.5 centimeters. So okay, we'll do 7.5 centimeters into 10 minus 2 meters square. And you change the field from 0.5 Tesla in 0.1 seconds. Yep. All right, so the induced EMF, and this kind of stuff is relevant. So when you turn on MRI machines, for instance, you turn off MRI machines, you're going from a strong field to a 0 field. And so you don't want to quench the field too fast. Okay, that's 10 to the power 4, that is 5, so, and that's 250, so this becomes 250 pi 7.5 square into 10 minus 4 volts. Okay. So the induced EMF is okay, so 4.42 volts. Okay. And of course, if you quench it in 1 second, it'll be 0.44 volts and so on. So the slower, the longer you take for the field to go to 0, the lower the EMF. Okay. So this problem says a single turn circular loop of wire of radius 50 millimeters lies in a plane perpendicular to a spatially uniform magnetic field. During a 0.1 second time interval, the magnitude of the field increases uniformly from 200 to 300 millitesla. Determine the EMF induced. Okay, so again, it's a similar problem. So here's a magnetic field, and circular loop of wire. Okay. And the magnetic field is increasing. Okay, so what will be the direction of the current, induced current? Can you guys figure it out? The field is increasing. So the induced current should be such that, what does Mr. Lenz say? The induced current should oppose this thing. So you want to produce a magnetic field in that direction. Okay? So the induced current will be in, okay? Okay. So the induced current, I induced, will be in that direction. Okay. All right. What is the direction of the induced current? Okay. The EMF is again, cosine theta is 0, so cosine 0 is 1. It's del B by del T times area. So 100 millitesla and change in 0.1 seconds, and the area is 25 millimeters. Okay. So this would be 1,000 millitesla, which would be 1 Tesla per second. So 1 Tesla per second times pi times 625 into 10 to the minus 6 volts. Okay, so, and all that works out to so roughly 2 millivolts. And for part B, we have already figured out the direction of the induced current. All right, so again, let's use Lenz's law to figure out the direction of the induced current. So in this case, so the blue dots are magnetic fields. The magnetic field is coming out of the sheet. Okay, if the conductor moves in this direction, what will be the direction of the induced current? Okay, so when the conductor moves in this direction, the flux through this loop is decreasing, and so you want to increase the flux through that loop. Okay, so the induced current will have to be in this direction, because you stick your fingers out in that direction and the flux magnetic field will come out of the plate. Okay, so the induced current will be in this direction. Okay, so this thing, what does this look like? Okay, again, the field is coming out, and this thing, the plane of this loop is parallel to the flux. There's no flux threading this thing. So as this thing is moving, the flux is not changing. No current is induced. Okay. All right, I have trouble with this one. Help me out with this one. Okay, so the flux, the magnetic field is coming out, and this thing is moving perpendicular to the, okay, yeah?
So it would be reverse clockwise, right?
Okay, so the flux is increasing in this direction, and you want to produce a flux in that direction.
So it would be clockwise?
Yeah, it would be clockwise. Okay? Did you guys understand that? Okay, so the magnetic field is coming out of the plane of the sheet, and you're moving this like that. So the flux in this direction is increasing, so you have to produce a magnetic field in that direction, and so the induced current has to be like that. Okay? All right, now let me ask you a harder question, well, slightly harder question. How long will this current be induced? Okay?
As long as it's moving, or
Okay, so let's say the ring is here, it's still moving. So once the entire ring is in the magnetic field, and even if it moves, now the flux is not changing. Okay, did you understand that? Okay. So the current is induced as long as the flux is changing. So as long as it's the entire thing, once the entire thing is inside the magnetic field, then the flux will stop changing. Okay? All right. Again, in this case, no induced current because there's no flux through this thing. Okay. And here, B is increasing. How about for this case? So B is in this direction. Okay, so you want to produce the induced current should produce a magnetic field into the sheet, induced field. Okay, so it should be like that. Okay. Okay, so the key thing is, Lenz's law says, induced current is such that it opposes the change that is producing it. Okay, that's the statement. That's the Lenz's law. So if the magnetic field is increasing in this direction, flux is increasing in that direction, you want an induced current which will oppose the change, meaning produce a magnetic field in that direction. Yeah. All right, we'll do one more problem and then we'll call it quits. How many of you have to do lab today? Okay, you're doing lab, okay. You guys have already done lab? Okay. Maybe we'll start lab early. We'll see. So a coil of 1,000 turns encloses an area of 25 centimeters squared. If it's rotated in 0.1 seconds from a position where its plane is perpendicular to the Earth's magnetic field to one where its plane is parallel to the field, what is the average EMF induced? Okay, so here's the coil, here's the magnetic field, and then what you do is you turn it like that. Okay, so the EMF induced is rate of change of flux. Okay. And so change in flux is delta T. The final flux is 0. Okay, and then we'll take the absolute value. Initial flux is NBA. N is the number of coil, B is the magnetic field, and A is the area of the coil. Yeah. So the average induced EMF is NBA divided by the time over which that change happened. Okay, 1,000 turns. The magnetic field is 6 times 10 to the minus 5 Tesla. Area is 25 centimeters square. And that's that many meters square. And the time is 0.01 seconds. All right, so let's take care of powers of 10. This is 10 minus 2, that makes it 10 minus 3, 10 minus 7, 10 minus 4, and 25. So 6 into 25 into 10 minus 4 volts. And this is 150, so 15 into 10 minus 3 volts, 15 millivolts. Okay. Okay. You took a 1,000 turn coil and turned it in 10 milliseconds in the Earth's magnetic field, and the maximum voltage you developed was 15 millivolts. Okay. All right, guys, so we'll stop here.